Alright, so this video will be an introduction to polar double integrals and how we can use them to find area and volume of polar curves, and how we can change our variables to polar coordinates to help make stuff easier. So here we have an area between two curves problem. In this case, we have four different curves we need to find the area of. So let's try finding it in rectangular coordinates. But if we do this, let's say we have these representative rectangles, one here, and another here. But you notice we run into a problem if we do representative rectangles this way, because we have this curve that goes down sloping as our lower bound, and this straight line as an upper bound. And but when we go a bit to the right here, then the bounds we have are different, where we have a different downward sloping line as our upper bound, but even the same lower bound. And then here, both of our bounds are different from the first one. So that seems like a big problem for us. And the same thing happens with horizontal representative rectangles, or the dx dy order. So that's why polar coordinate conversion comes in handy here, because if you notice, we have a sector that can be formed with theta's values. So let's call this alpha, and let's call this beta. And let's call this value theta, which corresponds to this small change between beta and alpha, or beta minus alpha. And our x-axis is the polar axis, which will correspond to theta equals 0. And here's theta equals pi over 2 in the y-axis. So the logic here is the same. We're going to partition the radius in a few ways. This will be similar to our representative rectangles in one direction, and as an analog to the other direction, we have representative sectors, which will be formed through theta values sampled here. And this doesn't necessarily have to be equal subintervals. It's preferred to have this random sampling of subintervals to determine the integral or the area of this polar curve. So you may recall that in Calc BC, we learned that the area of a polar curve, or between two polar curves, let's just simplify this, would be the integral of from a to alpha to beta, because we're doing this with respect to theta. We have these two values already, and you may remember 1/2 r squared d theta from your Calc BC class. So today we'll be deriving a double integral formula that is equivalent to what we have here. So let's just try to establish this conceptually. So we're going to take some points here and have r and theta associated with them. And now we're trying to find the area of this region, which we'll call capital R. You're going to have a delta r and delta theta associated with this one. And let's just draw this separately, so this sector separately, so you guys can see it without all these disturbances. Here we have the sector here with r and r1, r sub 1, r sub 2, and in between these two we have delta r, and r sub 2 is from here, and then r sub 1 ends at this sector. So that's just a rough drawing. Now we are going to try to find the area of this sector. So we know that the area of a sector in the circle would be pi r squared, because that's the area of a circle. But now we need to divide the theta over 2 pi, because we need to find the fraction of a circle that the sector represents. So, and let's just call this theta or delta theta to make this clear. So then the area of R would be pi. Let's just simplify the area formula so we can work with it. So take out pi, and then we have r squared theta over 2. And this would be r2 squared theta over 2 minus r1 squared theta over 2. And we know difference of squares, so let's simplify this to do and take out the theta over 2. And here we get r sub 2 squared minus r sub 1 squared. And we can put this in factor form. So r2 plus r1 and r2 minus r1. Now let's scroll down here and focus on this. And we can group this part together. And this represents the average of the radii here. So this radius, which would represent the central R of the region. And now we have r sub 2 minus r sub 1, which we've already established is delta r here. And we have theta, or delta theta. So let's simplify this to r, delta theta. And in an integral expression, we are going to have several subintervals and several r's that we're evaluating to get the area of this. So let's put this over an integral. So we have area equals a double integral on over r, and then r delta theta. And notice that if you set the bounds to theta, alpha and beta in this case, and r sub 1 and r sub 2, and integrate with respect to r first, so you get alpha to beta 1 half r squared from r sub 2 to r sub 1 and delta theta. And notice that this is just our Calc BC formula, in which we get after one step of allowing the double integral. And note that just like with rectangular, you can swap the order of integration. So this could also become theta as a function of r, and you have the two radii here. And this could become delta d theta dr. So switching the order of integration is definitely there. So now let's work over an example. So we're given a rose curve. So r equals 4 cosine 3 theta. So it would look like something like this, where you start with 4 and then it goes to 0. And then you get another petal here. And notice the way I'm tracing it. It doesn't go like this. You have to follow it smoothly like that. And that will be very important as we get into other examples, because even though you can just apply the double integral formula without splitting it, this could get into some conceptual gray areas that we should avoid to keep the intuition with the formula near its conceptual roots. So let's demonstrate this. So first, let's try to evaluate the area using the double integral. So notice that from 0 to pi over 6, it goes from cosine of 3 times 0 at 4 times 4, it is 4. But at pi over 6, then this thing becomes pi over 2, and cosine of that is 0. So that's where you're going to hit that spot. And then let's say we do pi over 4, which is further down that. You're going to get cosine of 3 pi over 4, which is less than 0. So you're going to have a negative r here. So notice that if we try to sample at pi over 4, you're not going to find any point on the curve. You're basically trying to map an r to the curve where the point on the curve doesn't exist there. Which is why we can only have positive r when we're defining our bounds. But let's try to solve the integral in a different way that it doesn't map onto any negative r's. So let's say we have positive r's only from, let's say, consider this petal where we have different dr and d theta. So let's see where this line is and that line is. And then we'll try to just get the area of that petal. So when is 4 cosine 3 theta equal to 0? In that case, we have a cosine of 3 theta equals 0, and 3 theta equals pi over 2 and negative pi over 2. And this would simplify to uh, negative pi over 6 and pi over 6. From here, let's put these inner bounds over the integral. So theta bounds. And for radius, we can just put in the function because that's equals r. So let's set up our double integral. And this would be 1/3 of the area because there's 3 petals. And then let's integrate from 0 to 4 cosine. And as always, we already derived this from the beginning, but r dr d theta. And notice that we have symmetry here in the Rose curve, that the area from 0 to pi over 6 is the same as from negative pi over 6 to 0. So we can simplify this even further. From 0 to pi over 6 now that we've brought the other symmetrical part out to the coefficient. And now let's evaluate this part of the integral. So we have 1/2 r squared. And notice this is already back to what we're familiar with doing in Calc BC. And also d theta. And we're going to substitute in the r squared. There's nothing for 0, so we can ignore that. So this would equal 6, the integral from 0 to pi over 6, times 8 cosine squared 3 theta d theta. And we can take out the 8 and just try to integrate cosine to the cubed. You integrate cosine squared from there. So let's simplify cosine squared so it's easier to work with. So cosine squared 3 theta. We can use the power reduction formula here. So the power reduction formula says the square of cosine is 1/2 plus 1/2 cosine of 2 times theta. In this case, it's 3 theta, so 2 times 3 theta would be 6 theta. And we can plug this in here. And this is a review of the integration techniques from BC. So the main technical part was in the setup, but I'll also demonstrate that because there's an r squared in the formula here, with the squared part, this is actually not going to matter if you go from 0 to pi, even though it crosses negative r's, because negative r whole squared is the same as r squared. But this is just a conceptual thing I want to mention, and it's by convention we only take positive r values. This will become theta over 2 plus 1/2 sine of 6 theta. I would take pi over 6 to 0. And the sine of pi and sine of 0 are both 0, so this term can be ignored entirely. And this would also be 0 on the second term, so 48 pi over 12 minus 0, and this would be 4 pi. Now let's demonstrate if we just integrate it from 0 to pi. So if we do 0 pi and the equation uh, and r dr data, we will get the 1/2 r squared from the integration with respect to r. And ultimately, you'll get the same result using the same integration techniques here. And let's just reuse uh, the integral result that we already found in the previous iteration of the exercise. And here, sine of 6 pi and sine of 0 are also both 0. And we get 8 times pi over 2, which is the same result that we got before. But note that even though this works computationally, you're tracing over points like pi over 4, and also stuff like uh, stuff like 3 pi over 4, which would no, it would also be invalid, but any point where it traces to a negative, so this angle would also be from 0 to pi, and this angle would also be not part of the grid. So uh, even though 3 power 4 actually is in there, but I was just giving examples of why this just not splitting the integral when you include negative points, even though it works and will give you the same answer, it's not actually uh, intuitive with respect to what we're trying to do with find the area of this curve. So that's all the example. That's the one example I had for finding polar area. For volume, you can do the same process as double integrals in rectangular coordinates, except you make sure to put the r drt data and not just leave it as drt data. Like for example, if you have a curve of a height over it, just put that height inside the integral like you do with an integral in rectangular coordinates. So thanks everyone for watching me demonstrate this, and I hope you have a great day.